All right, welcome to Lecture 25 on this course of algebraic topology. I'm Norman Wahlberger, and today I'm going to continue on with the fundamental group of a surface. So I remind you where we've been at. We have a surface, say M. We fixed a base point x0. We've been talking about paths on the surface, and in particular loops based at x0. And we have a notion of when two such loops are homotopic. All right? And if they're homotopic, then we can talk about the equivalence class or the equivalence type of that loop. And we have a way of combining two such types or classes. So if there's another loop, say beta at x0, then we can combine them or multiply them to get a new loop that goes like that. So that's alpha times beta. And so we have a multiplication. Alpha times beta. And we saw that that multiplication of paths or of loops gives a multiplication of equivalence classes or equivalence types by the rule. The class of alpha times the class of beta is the class of alpha times beta. And so now we have this fundamental object called the fundamental group. Of the surface M, based at the point x0. And what that is just the equivalence classes of loops alpha together with this multiplication of equivalence classes or equivalence types. And the first thing that we have to do today is to convince ourselves that this name is justified, that this object really is a group. Okay? So the theorem is that pi of, not g, pi of m. We have to convince ourselves that pi of m based at x0 is actually a group. In the technical sense of group theory within mathematics. All right, so there's three things basically that we have to prove. We've already noted that the product of two loops is another loop. So the closure property, which is often sometimes considered part of the group definition, is automatic here, so we don't need to check that. We need to check the existence of an identity element, we need to check the existence of an inverses, and we need to check associativity. Okay, so let's do those three things at a time. So first, the identity. So is there an identity element in this group? Well, it's pretty obvious that there is, and it's the constant loop. So the identity element is what we've been calling alpha 0. That's the constant loop, the loop that doesn't go anywhere, that just stays at x0. Okay. And so what we need to do is we need to prove that if we take this alpha 0 and we multiply it by any alpha, so that's the same as alpha 0 times alpha, that we get back alpha. And also we need to also check the same for the other way around. So how do we check that? Well, what's it really saying is that the loop alpha 0 times alpha is homotopic to alpha itself. So we have to find a homotopy between this path and this path. And a homotopy is represented by a square. Here's our surface M. We're looking for a homotopy, usually called H, say. that's got to go continuously from alpha 0 times alpha. And we can represent alpha 0 times alpha like this. This is the t variable. This is the s variable going from 0 to 1. And alpha 0 alpha, so that's going to be alpha 0 times alpha there. And up at the top is just alpha. So let's have a look at what these two loops do. So there's our point x0, let's say. There's our loop alpha. Our loop alpha 0 doesn't do anything, it just sits there. All right, so what is this loop represented by the bottom of this homotopy going to be? It's the path that for time t equals 0 to a half just sits there. And then at time t equals a half, it wakes up and it starts going around alpha twice as fast as alpha would normally do. Okay? We have to go continuously from that path to the path alpha, which is just the regular path of alpha. Okay, so how are we going to do that? Well, you could write down a formula, but it's perhaps easier if we just do something like this. Okay? I'm just going to draw some lines from this alpha to this alpha, and I can do it any way I want to, but I'll just sort of do it in a reasonably linear way. So what does this represent? It represents a continuous deformation. So if we have some intermediate step like that, what this means is that we're going to still sit at the constant loop, but not quite as long, only up to there. And then we're going to kick in and go along alpha, just according to this prescription here. So in other words, our movie consists of a sequence of paths where we're successively spending less time at x0 in the initial stage. Initially we have a half period, and that's going to be decreasing as we go up until eventually we're not spending any time at x0 and starting off immediately with alpha. So you could write out formulas for this. Okay, just sort of figure out the equations of these lines. You could actually write down a formula for the homotopy. But I don't see that there's much point. I hope it's reasonably clear what this diagram represents. A way of going continuously from this combination alpha 0 alpha to alpha itself. And that homotopy proves that alpha 0 times alpha is actually homotopic to alpha, and so alpha 0 times alpha in terms of the equivalence classes is equal to the class or the type of alpha. That's the first of our three things. So the second thing was we had to prove the existence of inverses. So here's our point x0. Here's a path, a loop, say alpha. I have to convince you that we can find another loop beta so that alpha times beta equals our identity element, equals the constant loop in homotopy, equal in homotopy. So the question is, given alpha, how to find beta, which is like going to be sort of the inverse of alpha. Well, the idea is to do the simplest possible thing. Beta is going to be the curve alpha reversed. So the answer is choose beta defined by beta of t equals alpha of 1 minus t. Just going going backwards along alpha. So but I now have to convince you then that we need to show that alpha times this beta actually is homotopic to the constant loop. In other words, that if I do the combination, start with alpha and then continue along with beta, that combined loop is actually homotopic to the constant. So I'm going to draw a homotopy diagram that illustrates that. So there's the halfway point. We're going to put alpha there and beta there. Beta is alpha backwards. And I need to convince you that this combination of alpha and then going back alpha is homotopic to the identity. To exhibit a smooth way of transiting or making a transition from this one to this one. All right, so let me represent it with a picture, a little bit like this. So here's some random intermediate point. Okay, what are we going to do at some random intermediate point, typically S? Well, we're going to stay where we are for the first section of it. And then we're going to, this is dotted here, we're just going to go parallel like this. And here we're going to, at the end, we're also going to be at alpha 0, and we're going to go parallel up here like this. Okay, what does this mean? Okay, so this means, so what's the recipe that represented by this line? It means, okay, the path is, you sit not doing nothing until this particular time. And then at this particular time, you start moving along alpha. So when this guy was here, you're now here. And as the curve alpha is going, you're moving along alpha. And you keep doing that until you get to this halfway point. We will not have gotten all the way to the end of alpha. You will only have gotten maybe 3/4 of the way. At that point, you stop, and you go back the way you came. Here, this point here is the same actual point on the surface. And then you're just going back along the reverse of alpha until this particular time when you're back at x0. And for the rest of the time, you just sit there. So let me show it to you in practice. So here is our point x0. Suppose the board is our surface, and here is our curve alpha. Okay, so here is what this transition looks like. First of all, here's the initial curve. Alpha followed by alpha inverse. That was the starting point. Okay? A little while later, the curve in the family looks like this. A little while later, it's like this one. Okay, it starts here, it sits for a while, and then it goes up like this. It doesn't get quite as far, and then it reverses. So it goes out and then comes back in. And once it gets there, it sits for a little while before the time t equals 1 occurs. A little while later, it sits for a longer there, and then goes like that. And what you can think of is you can just think of a piece of string that you've laid out. You've tacked it there, and you've laid out the string. But there you haven't tacked it down. You haven't tied it down. You're just wrapping it around like this. And then what you're doing is you're just pulling this string in and watching this double loop snake back to the origin, essentially. That's the meaning of this homotopy from alpha times alpha inverse to the identity, proving that alpha times this alpha inverse really is the identity in homotopy. And our third property is associativity. Which is that alpha times, well, we should do it at the level of things, that alpha times beta times gamma. If you have three things, then you make that combination first, and that's the same thing as alpha times beta times gamma. Now again, this is at the level of classes, so it's not that this path is exactly the same as this path. We're only claiming that this path is homotopic to this path. Okay, that's what we have to establish. So again, we'll do it with a picture of a homotopy. And down here, I will look at alpha times beta times gamma. And up here, we'll have alpha times beta times gamma. Over here is our surface. Let's draw a picture of these things. So there's x0. All right, we have some curve alpha. We have another curve beta. We have another curve, say, gamma. Although, in fact, they could overlap quite a lot, too. Doesn't really matter. Okay, what is alpha times beta times gamma? Well, remember how we multiplied paths. We divided our segment from 0 to 1 exactly in half. And we agreed that we're going to do the first part in the first half and the second part in the second half. So the first part here has to be alpha times beta. And the second half is going to be gamma. And what is alpha times beta? Well, that's what we get by going half alpha and then half beta. So this curve is really, we're going alpha very quick, beta very quick, actually 4 times the original speeds, and then gamma relatively leisurely, only twice the speed as originally. And we have to go from that combination to this one up here, which is alpha first, and then beta rather quickly, and gamma rather quickly. And we have to make a smooth transition from this combination to this combination. We'll have to find a homotopy. Okay, and here's how we do it. There. Okay, what does this mean? Well, it means that here's the path of alpha. So at every point here, it's registering where you are. So you're just going to connect these in some way. It doesn't matter, but let's do it linearly, which is the simplest to understand. We're just going to, instead of going from here to here, we're going to go smoothly from here to here. We're going to spend more and more time on the alpha portion as our curves go up. And the beta portion, well, we're just going to connect. That's just parallel. So we're just going to be doing the beta portion later, but at the same speed. And then the gamma portion has to be compressed. Again, you could write out formulas for these lines that connect these to these in terms of linear functions, but I don't see that it's too instructive. But if you actually had to tell a computer how to construct the homotopy, you would do it in that way with equations of lines connecting particular points here to the corresponding points up there. And so this diagram, maybe it's a little bit confusing now. I'll draw those segments. So that was a boundary segment, and that was the other boundary segment. So this illustrates that this is actually homotopic to this, and that these two are equal in homotopy. All right, so now let's have a look at some other fundamental groups. And probably a good place to start is our friend the torus. Well, we choose a point. Let's choose, okay, so that point right there, call it x0. We want to find some loops on this space. Now, a loop like this is not particularly interesting because that's homotopic to the constant. You can continuously deform that to the constant loop, so it's not going to be a non-trivial element in our group. To get something interesting, we should go around the hole that's there. That way we can't draw it back. So we'll get rid of that one. And we'll consider the loop, say that goes around here, around the back side, and comes back up here, and we're going to call that alpha. Now that is it is not homotopic to the constant. That's really a loop in the space. It's analogous to the going around once in the circle that we talked about when we were talking about the circle. In fact, you could now take powers of alpha. So if that was alpha, you could go alpha squared would be twice around, or alpha cubed would be going 3 times around, or alpha inverse would be once around the other side. But what makes this more interesting than the circle is that you can also go around in this direction. That's another loop, which we could call beta. And that's also a non-trivial loop, but it's different from alpha in some important way. And so we have these two fundamental kind of basic generators of the group. Alpha and beta. Now it turns out that there's a relation between alpha and beta, which is, okay, you can see it from this diagram, but it's a lot easier to see if we open up the torus and use our standard model of it as a square with opposite sides appropriately identified. So, for example, let me say, let's call that A and A, and say side B and side B. So reading around the outside, say starting from here, that would be A, B, A inverse, B inverse, which we recognize as a kind of our fundamental word representing a handle or a torus. And how do we get from here to here? Well, we just slice this torus, in fact, exactly along those two loops that I've just drawn. Right? If we first cut along alpha, that would be exactly the edge, say, that we could call A. And we could take that tube and fold it out to get a cylinder. And then if we sliced along beta, that would be just like slicing along B. So A and B here, these edges correspond to the loops alpha and beta that we've drawn. In particular, you can represent alpha by, say, this path. This path that I've just drawn here is really alpha. And it may not look like a closed loop, but you have to remember that this vertex, say we call it A, ended up being identified with this vertex and this vertex and this vertex. When you glue them together, all those 4 points coalesce. So this thing here, which doesn't look like a loop, in fact actually is a loop because it starts out from A and it ends at A. That's exactly the path or the loop alpha that I drew up there. And the path beta Draw it like that. There's beta. Because it goes along the edge that we've called B. And it also goes from A to A. It's a closed path. And now from this diagram we can see very clearly that there's a relation, because this loop here this one here is also alpha, because this edge and this edge are completely identified. So if we're going to call this alpha, this is also alpha. And because this edge is identified with this edge, then means that this path here is also beta. And so now what happens if we consider the combination of all four of these? If we start here and we go along here, and then along here, and then along here, and then along here. One path. What's that path? Well, that's going to be alpha, because that's what we did first, followed by beta, followed by alpha inverse, because it's alpha in the opposite direction. That's what we call the inverse. So times alpha inverse times, and then this one part here is beta inverse. And that particular combination has a very special property. Namely, this combination loop in yellow is obviously null homotopic. We can shrink it. We can shrink it because we can do that right in here. There, I've shrunk it a little bit. I've shrunk it some more. I've shrunk it some more. It's down to the constant loop. So this picture makes it obvious that if you go alpha, and then you go beta, and then you go alpha, and then you go beta, even on the torus, that combination can actually be shrunk homotopically to the constant. You could also see it on here if you thought about it enough. It's a good exercise to think about it. But it's very obvious in this polygonal representation that this thing here is actually equal to, or homotopic to, our constant loop. So this is an equation. It's an algebraic equation. If there weren't any multiplications here, we would usually write this just like this. And that's really the same as saying that alpha beta equals, well, if we multiply by beta on the right and then by alpha on the right, we would get to multiply by beta on the right first and then multiply by alpha on the right. It's really the same as this relation, that alpha beta equals beta alpha. And that's the relation of commutativity. That's telling us that alpha and beta are commuting here. It's commuting. And that means that this group is actually a commutative group. Commuting. So this makes describing the elements in this group a lot easier. So if you have an element in the group, and if I'm allowed to not write the stars everywhere, let's say I just write alpha cubed, beta cubed, alpha squared, beta cubed, alpha inverse, beta, that element there. If you're going to work in the algebra of this group, you're allowed to commute alphas and betas. So you could rewrite this as alpha squared times alpha inverse times beta cubed times beta. And then alpha squared times alpha inverse is going to be alpha, and beta cubed times beta is going to be beta fourth. So you can write every element ultimately in pi of the torus as alpha to the something and beta to the something else, where n and m are integers. So as a group, we could say it's Z cross Z. Now this idea here is, as pointed out, it's an idea that generalizes. So for example, if we look at the projective plane, then instead of trying to draw some complicated picture, it's best if we just stick with a polygonal representation. And there's a very simple polygonal representation that only has two edges. Our fundamental cross-cap, A. So remember, a projective plane can be obtained by taking a disk and gluing the boundary together so that this point is glued to this one, this is to this one, so opposite points are identified. And that means that this point here is actually the same as that point. And just as we did before, that means that this path is actually a loop. And that loop is actually exactly the same as this loop. It should be on the boundary. Those are the same loops because this edge is identified with this edge. And what happens here is something rather curious, is that when you take alpha times alpha, then you're talking about the combined loop that goes all the way around in this model, and that's obviously null homotopic in exactly the same reason as we had over there. You can continuously homotopy it within the space to the constant loop. So this is homotopic to the identity. So in this group is pi of the projective plane, really only has two elements in it. If we think of it as a set, it's got E and this alpha. And the multiplication, the only non-trivial multiplication, is that alpha squared is E. So it's, in terms of group theory, it's something called Z2. It's the same as the group like 0, 1 or minus 1. Minus 0, 1 mod 2 or 1 minus 1 multiplicatively, okay, depending on how you like to think about things. Multiplicative group that way, or an additive group this way, mod 2. Now this is an example of what's called torsion, where you have an element which has a finite power equaling the identity element. So alpha to the k for some k equals the identity. That's torsion. That's not happening over in the torus. It's not happening with the circle. With the torus or the circle, you take any element and you keep taking powers. You're getting more and more complicated loops. Okay, so let me give you a few problems. Problem 26. Describe the fundamental group of the Mobius band. And B, fundamental group of the Klein bottle. And C, maybe a bit more complicated, fundamental group of the two-hole torus. All right, so next time we're going to look at an interesting application of fundamental group to covering spaces, right, where we're looking at the spaces which can sit above a topological space in certain situations. So I'll see you then.